where curiosity gets cozy and science whispers beneath the stars. Tonight we're travelling back, not just hundreds or thousands of years, but billions, to a time when the sky was a stranger to blue and the air would have choked us in a single breath. And yet somehow that toxic world gave rise to the conditions that would one day let birds fly, whales sing, and you lie here tonight with your eyes slowly closing. Our question, then, is as vast as it is peculiar. How important was the Great Oxidation Event? That quiet, ancient moment when life rewrote the atmosphere and in doing so, nearly destroyed itself. But before we tumble down that oxygen-rich rabbit hole, let me ask, where in the world are you listening from? And is it morning, night, or somewhere wonderfully in between? If you find these slow journeys through deep time comforting or curious, a like or a subscribe is always deeply appreciated. It helps this sleepy little science nook find more fellow wanderers. So settle in, slow your thoughts, and let's begin. Because this story, this quiet revolution, started not with a bang, but with a breath. Roughly 2.5 billion years ago, our planet changed its mind about the kind of place it wanted to be, and almost everything alive at the time paid the price. Sometimes science begins not with a lab or a lecture, but with a puzzled glance at something that refuses to behave, a twitch of a compass needle in the middle of nowhere, a strange colour in a slice of ancient rock, a whisper from the past embedded in stone. It was in places like the Canadian Shield, where Earth's bones lie bare, that geologists began to notice something odd. Layers of iron-rich rock stretching for kilometres, banded in repeating stripes, grey, red, grey, red, like the planet was trying to send a message in Morse code. These banded iron formations, as they'd come to be called, were old, ancient even, but more than that, they were mysterious. Why did they form only during certain windows of deep time, and why, after billions of years, did they stop? Elsewhere, scientists noticed something just as strange: sulfur in sediment, telling stories through isotopes, tiny inclusions trapped in ancient zircon crystals, clues that didn't quite fit the atmosphere we live in now. Then, of course, there was the absence, the eerie lack of certain kinds of rocks, the missing signs of rust, the chemical silence in the record of oxygen. And yet, despite this silence, the signs kept whispering. In the late 20th century, researchers like Preston Cloud and James Lovelock began to piece together a grander narrative. They weren't looking at local quirks anymore. They were unravelling a planetary transformation, one that didn't just alter the chemistry of air and ocean, but changed the very nature of life itself, the Great Oxidation Event, or if you're feeling formal, the GOE. Not an explosion, not a meteor, but a slow, creeping change that turned the Earth from a world ruled by shadows and sulphur into a stage where oxygen could breathe. To get there, though, we have to go back, far back, to a time when Earth was almost unrecognisable. There were no trees, no grass, no insects, no animals or fungi or flowers, no ozone layer to paint the sky its familiar blue. The continents were small and scattered like crumbs on a vast ocean. The sun was dimmer than it is today, filtered through a haze of volcanic gases and methane. The air would have smelled strange, heavy with sulphur and iron and carbon. Breathing it would have been like trying to inhale a bonfire underwater, and yet there was life, fragile, simple, invisible to the naked eye. Microbes mostly. Tiny cells without nuclei, prokaryotes. Life that clung to hydrothermal vents in the deep sea, basked in chemical soups along the shore, or floated through shallow waters like aimless specks. They were ancient, hardy, and in many ways alien to us. But one group of them, small, stubborn, and utterly revolutionary, was about to make the biggest mistake in the history of life. Cyanobacteria. Not much to look at. blue-green in colour mostly, a kind of aquatic slime if we're being uncharitable. But these microbes had figured out something extraordinary. They had learned how to harness sunlight. Using water and carbon dioxide, they could turn photons into fuel, releasing a byproduct into the water and eventually the atmosphere. That byproduct was oxygen. Now to us, oxygen is comfort. It's candles, breath, life. But to the microbial world of early Earth, oxygen was something else entirely. It was a poison. Highly reactive, chemically aggressive, and deeply incompatible with the anaerobic lifestyle that most early life depended on. Releasing it into the environment was like dumping acid into a swimming pool. Slowly, the oceans began to rust. Iron dissolved in seawater reacted with the oxygen, forming insoluble compounds that sank to the bottom and layered themselves into the banded formations geologists would one day find and puzzle over. At first, it was manageable. The iron in the oceans acted like a buffer, soaking up the excess oxygen, a chemical sponge if you will, but eventually the sponge got saturated, the rusting slowed, and the oxygen had nowhere left to go except up, into the atmosphere, and that's when everything started to unravel. But let's not rush. Let's stay with the puzzle a moment longer. In South Africa's Transvaal supergroup, in the Pilbara of Western Australia, in the greenstone belts of the Canadian Shield. Across all these places, rock layers began to tell the same quiet story. Around 2.45 billion years ago, give or take 100 million years, because in geology time is generous, the chemical fingerprints of Earth's atmosphere shifted. Sulfur isotopes split in new ways. Red beds, oxidized sediments began to appear. The mass-independent fractionation of sulfur, a process that only occurs in an oxygen-free atmosphere, vanished from the record. It wasn't a bang or a bolt from the blue. It was a tipping point, a planetary seesaw beginning to tilt. The Great Oxidation Event wasn't a single day or year or even century. It was a saga, a slow, jagged transformation that may have unfolded over tens or even hundreds of millions of years, sometimes advancing, sometimes stalling, like a tide hesitating at the edge of the shore. But the end result was unmistakable. The planet changed its breath, and life would never be the same. Now, from our perch in the present, oxygen seems like a gift. It powers our muscles, feeds our fires, lets our brains string these very words together. But back then, for the majority of life, it was a disaster. Imagine being a microbe, evolved perfectly for a world without oxygen. For billions of years, your enzymes had danced to a different tune, one of fermentation, sulfur reduction, and methane metabolism. And now, this strange new gas was flooding your environment, reacting with your molecules, breaking your bonds, killing your neighbours. Some tried to hide, retreating into anoxic pockets deep in mud and sediment, or into the guts of other organisms. Others died in vast invisible numbers. It was, quite possibly, Earth's first mass extinction. We have no fossil record of screams, of course, no tombstones for single-celled martyrs, but the geochemical record carries the echoes: carbon isotope excursions, disrupted sulfur cycles, a plummet in atmospheric methane, one of the key greenhouse gases of early Earth. And with the methane gone, the planet cooled drastically. Some scientists believe the Great Oxidation Event helped trigger what's known as the Huronian glaciation, an ancient worldwide freeze that may have covered much of the Earth in ice, a snowball planet shimmering white beneath a pale sun. The very oxygen that made future complexity possible may have plunged the Earth into a global deep freeze. Talk about growing pains, but not everything died. Some microbes adapted, a few even thrived. Oxygen, after all, is an excellent source of energy, if you know how to tame it. Life began to explore new biochemistries. The ancestors of modern eukaryotes may have emerged during or after this time, setting the stage for more complex cells and eventually multicellular life. It wasn't just an extinction, it was a reorganization, a reboot. And as we trace the echoes through rock and time, we find ourselves circling back to the same quiet question. Why did it happen then? Why did cyanobacteria suddenly tip the balance? Had they just reached critical mass? Had the Earth's chemistry changed in subtle, invisible ways? Was it tectonics? Volcanism? A quirk of plate motion that opened new shallow seas for photosynthesizers to thrive in? Like many ancient mysteries, the answer is probably yes, to all of it. Earth doesn't do simple, and neither does life. So the Great Oxidation Event wasn't a single switch flipped in the dark. It was a murmur building into a crescendo, a chorus of changes, some accidental, some inevitable, a planet reimagining itself, cell by cell, breath by breath. And the strangest part, it wasn't the last time oxygen would change everything, not by a long shot. Long before the skies turned blue, before forests whispered in the wind or fish flicked silver tails through coral reefs, Earth was something else entirely. A restless, brooding planet with a wild heart and no clear direction. If you could step back 3 billion years, just for a moment, you wouldn't recognize it. You wouldn't even survive it. The air would burn your lungs if you tried to breathe it. The ocean would poison you slowly with metals and acids your body couldn't tolerate. The land, such as it was barely land at all, just fragments of rock jutting out of an endless greenish sea. There were no trees to cast shadows, no grass to soften your step, no sounds but the hiss of steam, the rush of tides, and the occasional groan of the earth itself. And yet, it was alive, not with creatures that walked or flew, but with things that pulsed, divided, absorbed, and transformed. Microbial life, the quiet architects of the biosphere. To understand the Great Oxidation Event, we first have to understand the world it tried to change, a world of shadows and smoke, of deep water and chemical hunger, a world where life was simple, but astonishingly creative in the ways it fed, moved, and survived. The atmosphere in those days was thick with volcanic gases, carbon dioxide, methane, ammonia, hydrogen sulfide. There was no ozone layer to shield the surface from ultraviolet radiation, no oxygen to bind with iron or paint the rocks red. The sky might have been tinted orange or pink at times, depending on what the volcanoes had been up to that day. Clouds rolled across a sun that was weaker than it is now, but still fierce enough to beat down on the shallow seas. And those seas were strange, warm, perhaps, turbulent, loaded with dissolved minerals that today would send alarms blaring in a chemistry lab. Iron, nickel, sulfur, arsenic. The ocean was like a cauldron of potential, a chemical playground where life first began and continued to evolve, one molecule at a time. Down near hydrothermal vents, communities of archaea and bacteria thrived in the heat and darkness. These deep-sea chimneys exhaled a cocktail of energy-rich compounds, and microbial life learned to make use of them. They didn't need sunlight. They had chemosynthesis, a way to live off the raw exhaust of the Earth's interior. To them, sunlight was a rumour, an irrelevant detail. In other parts of the ocean, other strategies flourished. Some microbes lived on sulfur, others fermented, some split hydrogen or feasted on methane. Metabolism in the ancient world was a wildly varied buffet of survival options, and in that biochemical chaos, evolution had room to experiment. And then, quietly, something extraordinary happened. Some microbes learned to use light. They weren't the first to do so. Primitive forms of photosynthesis had likely emerged earlier, ones that didn't produce oxygen. But cyanobacteria were different. They had cracked a new code. They figured out how to use water as a source of electrons, splitting it apart with the help of sunlight. In doing so, they produced oxygen, not as food, not as fuel, but as waste. And here is where the story takes its quiet, fateful turn. Because in a world without oxygen, releasing it was like setting fire to a room full of paper. It changed everything. At first, though, it didn't seem like much. The oceans were full of dissolved iron, which eagerly absorbed the oxygen and rusted into solid particles that drifted to the sea floor. That rust would one day become the banded iron formations that puzzled modern geologists. But back then, it was just chemistry doing its thing. Cyanobacteria, unaware of the future, multiplied. They formed mats in shallow seas, layered structures called stromatolites that still exist today, like wrinkles in the fossil record. They basked in the sunlight, churned out oxygen, and filled the water with slow, invisible change. Meanwhile, the land was silent. No birds, no bugs, just rock, wind, and time. Imagine standing on the edge of an ancient continent, barely more than a rocky plateau, surrounded by warm, metal-rich ocean. The sky is dusky, painted in strange hues. The wind carries a tang of sulphur. Below you, in tidal pools, slimy films of cyanobacteria ripple gently, exhaling a gas they can't use and barely notice. That gas begins to accumulate, not in a rush, but like the tide, relentless, patient and world-altering. Life, you see, does not always know what it's doing. It does not ask permission before changing the rules. It just follows the chemistry, and the consequences come later. That's what makes the ancient world so mesmerizing. Not just how different it was, but how obliviously powerful the smallest organisms could be. The oceans were Earth's first lungs. Before forests breathed, before plankton danced under moonlight, the sea was where gases mixed, reacted, and evolved. Every molecule of oxygen that reached the air had to first push through layers of water, sediment and resistance, but it kept coming. Over millions of years, as the iron in the ocean was used up, oxygen began to accumulate. Slowly, gradually, it tipped the balance. The atmosphere began to change. Not all at once. Earth doesn't do anything quickly, but the direction was set. The cyanobacteria kept photosynthesizing, blissfully unaware that they were transforming the planet. Their waste, lethal to many of their microbial neighbours, spread into the air. The oceans rusted. The sky began to clear. And life, simple, microbial, ancient life, had to choose: adapt, retreat, or die. It's a strange thing to picture. We think of mass extinctions as violent cataclysms, asteroids, firestorms, global winters. But this was different. It was a suffocation by abundance, a purge by progress. Oxygen was too reactive. It damaged the delicate biochemistry of anaerobic cells. It disrupted ancient cycles of sulfur and methane. It caused death by evolution. Some microbes found ways to hide. Others evolved defences, enzymes that neutralised oxygen, metabolic detours that made use of it. But many simply vanished, lost to time, unrecorded except in the shifting chemistry of ancient sediments. And the land, still lifeless, still waiting. It wouldn't be colonised for billions of years, but the groundwork was being laid, slowly, quietly. With each molecule of oxygen released, the Earth was being primed for something new. Some of that oxygen reacted with methane, a potent greenhouse gas, and helped trigger a global cooling. The Earth, once a steamy greenhouse, began to freeze. Ice crept toward the equator. The Snowball Earth hypothesis suggests that this was no ordinary ice age, but a planetary slumber. A deep freeze that might have lasted millions of years. Even in this frozen silence, life endured. Microbes clung to thermal vents. Pockets of water beneath the ice remained liquid, protected by heat and pressure. Cyanobacteria may have persisted in brine channels, in sunlit cracks, in any refuge where light could still reach. Oxygen production may have slowed, but it didn't stop. And when the ice finally receded, the planet emerged into a new balance. A world where oxygen was no longer a trace impurity, but a permanent presence. This was the beginning of something vast. In the distant future, it would make possible the rise of complex cells, eukaryotes with internal structures like tiny cities. It would allow multicellularity, specialization, nervous systems, movement, behavior, thought. But all of that was still eons away. For now, Earth was just breathing, slowly, learning how to handle its new atmosphere, adjusting. It would take hundreds of millions of years before oxygen reached modern levels, and even then, it wouldn't be a straight line. There were reversals, collapses, periods of stagnation and rebound. Some call this the oxygen overshoot. Others speak of whiffs and pulses of oxygen that came and went, like the breath of a sleeper stirring in bed. But something had changed irreversibly. The biosphere had discovered a new way to live, and with it came the possibility of everything that followed. So the ancient world was not a dead place. It was not empty. It was full of anticipation, of chemical potential, of a strange microbial hope. It was a world preparing itself, not consciously, not deliberately, but through the endless blind dance of molecules and mutation, preparing for eyes that would one day gaze up at stars, for hands that would touch stone, for voices that would tell stories about things long gone. The Earth before the Great Oxidation was quiet, yes, but not still. It was changing, one breath at a time, and that breath changed the world. There's something beautifully ironic about what caused the first great biological crisis on Earth. It wasn't a meteor strike or a volcanic eruption. It wasn't war between creatures or a shift in the planet's magnetic field. No, it was photosynthesis, that serene, sunlit process that schoolbooks present like a cheerful cycle. Sunlight, water, carbon dioxide, plants making oxygen. That quiet miracle was at first a death sentence. To understand how that happened, we need to look more closely at the culprit. Oxygen. Today it feels familiar, safe. It surrounds us, lives in our blood, fuels our fires. But that's because we've evolved to dance with it, to breathe it in and use it with elegant, almost unconscious precision. To early life, though, oxygen was a wild thing, a loose cannon, a molecular vandal. Chemically, it's greedy. It pulls electrons like a magnet, tearing through delicate bonds, disrupting metabolic pathways, oxidizing lipids, damaging DNA. In a world of anaerobic metabolism, where life got its energy by gently nudging molecules, not ripping them apart, oxygen was chaos. And yet cyanobacteria made it, not as a mistake, but as a byproduct, a side effect of innovation. Water, you see, is not an easy molecule to split. Its hydrogen atoms cling tightly to oxygen, and breaking them apart takes energy. Cyanobacteria learned how to use sunlight to do just that, pulling electrons from water and using them to drive the machinery of life. The waste, the thing they threw away once they'd stolen what they needed, was O2. At first, this wasn't a problem. The oceans were full of ferrous iron in a soluble form. That iron eagerly bonded with the free oxygen, forming iron oxide or rust, which precipitated out and settled on the ocean floor. This rusting process acted like a planetary filter, scrubbing the oxygen out before it could do any real harm to the atmosphere. This is how the banded iron formations formed, layer upon layer of chemical reactions rippling outward from tiny mats of microbes. The bands speak of fluctuating conditions, times when oxygen was produced, then times when it wasn't, perhaps tied to seasonal cycles, ocean currents, volcanic activity. The planet inhaling and exhaling chemically. But the iron couldn't last forever. As cyanobacteria spread, their populations exploded in shallow seas and warm lagoons. They blanketed tidal flats and clung to rocks. With each replication, each new mat, they released more oxygen. Slowly, the supply of dissolved iron was used up. Once the oxygen had no more iron to bind with, it started dissolving into the ocean itself, and then, gradually, into the air. The buffer was broken. From here, things moved faster. Not fast by our standards, but by Earth's usual pace. This was a sprint. With the iron no longer able to mop up the mess, oxygen began to accumulate in the atmosphere. It didn't surge all at once. It came in fits and starts, in pulses and whiffs. But the direction was clear. Each generation of cyanobacteria added more. Each geochemical cycle bent a little further in the direction of oxidation, and then came the first consequences. Methane, the main greenhouse gas of early Earth, is particularly sensitive to oxygen. It reacts with it, breaking down into carbon dioxide and water vapour. CO2 is also a greenhouse gas, but not nearly as powerful, so as oxygen rose, methane fell. And as methane fell, the planet began to cool. This cooling wasn't subtle. It wasn't a gentle evening breeze or a longer winter. It was the kind of cold that reaches into the bones of continents. The Huronian glaciation began, perhaps the longest and most severe ice age in Earth's history. Ice advanced across the surface of the planet. Glaciers grew. Oceans may have frozen from pole to equator. Whether it was a complete snowball Earth or a slush ball with some open water near the equator is still debated. But the point is the same. The Earth froze, and it may have stayed that way for tens of millions of years. The cause? A biological revolution. Cyanobacteria didn't mean to cause an ice age. They were just doing what worked. But the ripple effects of their oxygen overflow tore through the climate, through the chemistry of the ocean, and through the fragile network of microbial ecosystems that had held Earth together since the Archean. There are few fossils from this time, but we can read the rocks. Isotope ratios shifted. Ancient soils, paleosols, began to show signs of oxidation. Red beds formed on land for the first time, telling us that oxygen was now stable in the atmosphere. Sulfur isotopes, once fractionated by photochemical reactions in an anoxic atmosphere, now followed different patterns, signs that UV light was being filtered, that ozone, made from oxygen, was forming a protective shield in the upper atmosphere. Ozone, the side effect of a side effect. A gas made from oxygen that shields the Earth from deadly UV radiation. Without it, life on land could never survive. But it didn't appear because of foresight. It appeared because the chemistry demanded it. Oxygen built up, and some of it formed O3. And with that, Earth gained not just breathable air, but protection. Meanwhile, underground, deep in sediments, life was scrambling. Anaerobes, organisms that couldn't tolerate oxygen, began to vanish. Many had no defences, no enzymes to break down reactive oxygen species, no strategies for avoiding the creeping tide of toxicity. For them, the future was a narrowing corridor of safety, a retreat into mud, into the deep, into any place where oxygen had not yet arrived. Others fought back. The first antioxidant defences began to evolve. Catalyses, peroxidases, superoxide dismutases. These proteins allowed cells to manage the chaos, to detoxify their environment, to survive. Still others embraced the enemy. They rewired their metabolism to use oxygen, not avoid it. Aerobic respiration was born, a process far more efficient than anaerobic fermentation. It yielded more energy per molecule of glucose, more ATP, more bang for the buck. These cells could grow faster, repair damage better, compete more successfully. Oxygen, in short, became a tool. It wasn't easy. The transition was brutal. But the rewards were enormous, and it set the stage for a more complex world. This is where the first hints of eukaryotes begin to appear in the fossil record. Not definitive, not conclusive, but suggestive. Larger cells, internal compartments, the stirrings of complexity, and behind it all, oxygen making it possible. Oxygen doesn't just allow for more efficient energy production, it enables structural innovation, multicellularity, communication, differentiation, the development of tissues, nerves, muscles. All of that would come much later, but the door had been cracked open. The triggering event was now a global cascade. It began with cyanobacteria, sunlit and slimy. It passed through chemistry, rusting oceans, altered gases, shifting climates. It echoed through extinction, microbial die-offs, ecosystem collapse, and it ended in transformation. Earth became a new kind of planet, no longer just a place for sulfur-huffing extremophiles and methane-breathing archaeans, but a place where the future was possible, where complexity could arise, where life could stretch out, evolve new tricks, and one day, walk. But we're getting ahead of ourselves. First, Earth had to recover from its own evolution. The aftermath of the Great Oxidation Event was not a triumphant sunrise, but something quieter, stranger, more uncertain. Oxygen, though rising, was still fragile. It had appeared, yes, but it hadn't yet taken hold. Think of it like a match struck in the wind. There was firelight, but not yet warmth, not permanence. Oxygen levels may have spiked and then fallen, then spiked again. Earth seemed unsure what to do with this new element. Was it a blessing? A threat? The atmosphere wobbled in and out of balance, like a tightrope walker with no net. This wobble left fingerprints. There's evidence for what scientists call the oxygen overshoot hypothesis. After the initial rise, oxygen may have surged past its equilibrium, triggering mass die-offs, ice ages, and global reorganization, only to fall again as the planet's systems tried to absorb the change. For a time, the world may have flickered between oxygenated and anoxic states, like a lighthouse beam caught in fog, a planet with growing pains, a biosphere learning to breathe. It's here, in this awkward adolescence of the planet, that Earth began laying down some of its deepest geochemical habits. Today, our world is defined by cycles: the carbon cycle, the sulfur cycle, the nitrogen cycle. All of these are bound to oxygen now. But back then, those cycles were just forming. As oxygen slowly integrated into the biosphere, it rewrote the rules of recycling. Sulfur, for instance, shifted dramatically. In anoxic conditions, sulfur was handled mainly by microbes through a process known as sulfate reduction. But with oxygen around, new pathways opened. Sulfates were oxidized, reshuffled, bound into rocks. The sulfur isotope record, tiny variations in atomic weight, tells us that these shifts were not just local, but global. Carbon too began to behave differently. Before oxygen, carbon tended to get buried as organic matter, slowly, inefficiently, locked away in sediments. But with oxygen, decomposition became turbocharged. Organic matter could now be rapidly broken down and recycled. The biosphere learned to clean up after itself. This may sound like chemistry, and it is, but it's also storytelling. Because every atom of carbon or sulfur that moves through a system carries with it a history, a memory. And by tracing those atoms today, scientists can reconstruct scenes from a world that no longer exists. Meanwhile, the oceans began to stratify. With oxygen in the air, surface waters began to carry it too. But the deep ocean, isolated, dense, still, remained anoxic for much longer. This created chemical gradients, ecological frontiers. Life had to specialize. Microbes that could tolerate oxygen clustered in the shallows, basking in sunlight. Anaerobes, banished by oxidation, retreated into darker, deeper places. Some of them stayed there, unchanged for billions of years. They still exist today, in mud, in our guts, in hydrothermal vents, ghosts of the Archean, still breathing like they did when the world was young. But on the surface, the air was changing, slowly, inevitably. Volcanic gases began to react with oxygen, forming acidic aerosols that cooled the planet. Rocks began to weather differently. Oxidation, after all, affects everything. Iron-rich minerals on land began to rust. Soils changed. The colour of the landscape may have shifted, from darker, reduced minerals to lighter, oxidized hues. Earth's palette evolved, and above it all, the sky was changing too. Before oxygen, Earth had no ozone layer. UV radiation streamed down, unhindered, breaking apart molecules, sterilizing land surfaces. But as oxygen accumulated, some of it reacted to form ozone, O3. This ozone collected in the stratosphere, forming a thin but powerful shield. With it, the surface became safer. UV levels dropped. For the first time, life could begin to consider, slowly, over vast time, moving beyond the sea. It would be a long time still before that happened, but the stage was set. There's something almost theatrical about it. The air grows breathable, the sky turns blue, the ocean clears, and in the wings, life waits, watching, breathing, evolving. But let's not mistake this for a smooth transition. There were setbacks. After the initial rise in oxygen, Earth may have experienced a kind of pause, a period called the Boring Billion, a time between roughly 1.8 and 0.8 billion years ago, when oxygen levels plateaued, life stayed relatively simple, and not much seemed to happen. The world was stable, yes, but static. Cyanobacteria kept photosynthesizing. Eukaryotes existed but stayed small. It's as if evolution was taking a breath before its next leap. Why the pause? Some theories suggest a kind of chemical stalemate. The weathering of rocks may have absorbed oxygen as fast as it was produced. Organic carbon burial, essential for sustaining atmospheric O2, may have declined. Oceanic conditions may have favoured oxygen sinks over sources. Whatever the cause, oxygen remained at low levels, enough to matter, not enough to transform. But that too would change. In time, tectonics would shift. Continents would grow. Nutrients like phosphorus and iron would flood into shallow seas, fertilizing blooms of photosynthetic organisms. With each bloom, more oxygen. With each extinction, more carbon buried. Slowly, steadily, the balance would tilt again, and when it did, it tilted fast. Oxygen would surge again around 800 to 600 million years ago, this time for good. Complex multicellular life would emerge, nervous systems, predators, skeletons. The Cambrian explosion would burst forth like fireworks after a long silence, but none of it, not a single fin, feather, or pharynx, could have evolved without the oxygen laid down billions of years earlier. That's the irony, and the legacy. The Great Oxidation Event did not build life's complexity directly. It cleared the rubble, it rewired the planet, it forced evolution to reckon with a new kind of molecule, and in doing so, it gave life a challenge. Adapt or vanish, resist or evolve. Some organisms failed that test, others survived. A few became something more. You and I are the descendants of those survivors. Our mitochondria, the tiny power plants inside our cells, still bear the signature of that choice. They use oxygen to break down food, to make energy, to keep us warm, awake, alive. Every breath you take is a quiet affirmation of something that happened 2.5 billion years ago. Every heartbeat is a memory of a microbial decision amplified by deep time. And yet the story is still unfolding. Even today, the oxygen in our atmosphere isn't guaranteed. It's balanced precariously between sources and sinks, between photosynthesis and respiration, between the burning of forests and the burial of carbon. If plants stopped growing, or if too much organic matter decomposed at once, oxygen levels could fall. We are stewards now, not just of ecosystems, but of the very chemistry that makes breath possible. The Great Oxidation Event wasn't just a change in the air, it was a change in possibility. It took a planet ruled by chemistry and gave it over to biology. It gave time a new flavour, a new tempo. It whispered to life, grow, multiply, try. It opened the door, and eventually, we walked through it. It began as a breath, one microbe exhaling into the sea, then another, then millions. And slowly, invisibly, Earth began to change. But the Great Oxidation Event wasn't a simple switch. It was more like a chain reaction, each new molecule of oxygen setting off a series of consequences. some immediate, some unfolding over eons. Imagine dropping a single pebble into a pond and watching the ripples travel outward, not just across the water, but into the sky, into the soil, into the very blueprint of life. At first, oxygen was absorbed quietly, its reactivity hidden beneath the waves. But once it began to build in the atmosphere, it collided with everything. Methane was one of its first victims. Before oxygen, methane was one of Earth's dominant greenhouse gases. It kept the planet warm despite a faint young sun, wrapping the world in a gentle thermal blanket. But oxygen reacts readily with methane, breaking it down into water and carbon dioxide. And while CO2 can trap heat, it's far less potent than methane. The result was a dramatic cooling. Glaciers grew, ice advanced, oceans froze. The Huronian glaciation is considered by many to be Earth's first major ice age and perhaps its longest. It may have lasted for 300 million years. 300 million years of cold silence, of sun glinting off white snow that stretched from pole to pole. Some models suggest Earth may have become a true snowball planet, with ice sheets reaching the equator, a world wrapped in frost still spinning beneath a distant star. The irony, of course, is that this freeze was caused by life. Cyanobacteria were still photosynthesizing, still releasing oxygen. But their unintended climate shift nearly wiped out the rest of life on Earth. Organisms adapted to warm, reducing conditions suddenly found themselves stranded in a frozen, oxygen-rich world. Many died. Others clung to survival in pockets of liquid water, near volcanic vents, beneath ice-covered seas, in thin films beneath snow and rock. Earth was not dead, but it was quiet. During this frozen epoch, the chemical gears of the planet kept turning. Volcanic eruptions continued beneath the ice, belching CO2 into the atmosphere. Over time, this greenhouse gas began to accumulate again. With methane mostly gone and oxygen newly dominant, the planet's thermostat struggled to find its balance. Eventually, the build-up of CO2 would tip the scale once more. The ice would melt, the snowball would crack. But Earth did not return to what it was, because oxygen was still here, and it was beginning to settle in. With the ice retreating and the oceans mixing again, new interactions emerged. Sunlight reached deeper into the seas, nutrients stirred from the depths, oxygen began to penetrate surface waters more thoroughly, and with this, new habitats formed. Gradients of chemistry, oxygen above, anoxia below, created zones where new kinds of life could thrive. Microbes evolved to take advantage of these layers. Some formed symbiotic relationships. Others adapted to rising oxygen levels, developing metabolic pathways that could use it rather than flee from it. This shift gave rise to a new biochemical framework, aerobic respiration. Compared to anaerobic pathways, aerobic respiration is a powerhouse. It yields far more energy from each molecule of food. This allowed organisms to grow larger, to divide faster, to build more complex internal machinery. For the first time, life had the tools to scale up, but with energy comes vulnerability. Oxygen, while powerful, is still dangerous. It creates reactive oxygen species, molecules that damage DNA, proteins and membranes. To survive, organisms had to evolve defense systems, antioxidants, repair enzymes, protective barriers. The biological arms race had begun. The oceans themselves began to stratify further. Surface waters, now rich in oxygen, supported new communities, but deeper layers remained anoxic for millions of years. This created a dual world, an oxygenated sky and upper ocean, and a toxic, reducing deep sea. These redox boundaries shaped the evolution of life, forcing adaptations that would echo through evolutionary history. At the same time, Earth's crust was responding. As oxygen began to react with iron and other minerals on land, the planet itself started to rust. This process of chemical weathering transformed soils, altered river chemistry, and influenced how nutrients flowed into the ocean. And it wasn't just rock that changed. the carbon cycle began to shift. Before oxygen, organic carbon, produced by photosynthesis, was often buried in sediments without fully decomposing. But with oxygen around, much of this carbon could now be broken down, releasing CO2 back into the atmosphere. This feedback loop stabilised climate, but it also tied atmospheric oxygen levels to the burial of organic carbon. A delicate dance began. The more carbon that got buried, the more oxygen could accumulate. The more oxygen built up, the more efficient decomposition became. This cycle still governs our world today. Meanwhile, sulfur, another key player, found itself caught in the middle. In an anoxic world, sulfur circulated primarily in reduced forms like hydrogen sulfide, but with oxygen, it began forming sulfate, which could be used by new types of microbes and incorporated into different minerals. These sulfur transitions are etched into the isotope record, offering clues to oxygen's rise and the subsequent chemical reorganization of the biosphere. All of this, these countless interactions, weren't simply chemical, they were ecological, they were evolutionary. Oxygen wasn't just an atmospheric event, it was a pressure that reshaped life's possibilities. It rewarded those who adapted, it erased those who didn't. It rewrote what life could be, and while the most obvious changes happened in the ocean, the land was quietly preparing too. The formation of an ozone layer, created by high-altitude reactions between oxygen and ultraviolet light, marked a profound shift in the planet's surface conditions. For the first time, UV radiation was significantly reduced at ground level. This didn't immediately lead to life on land. There were no plants or animals yet, but it made the idea of life beyond the ocean possible. The atmosphere, once a barrier, was becoming a bridge. Ozone wasn't the only innovation. With higher oxygen levels came the potential for new mineral formations. Many of the world's most colourful and familiar minerals, such as iron oxides, manganese nodules, and even certain types of clays, only form in oxygen-rich conditions. The very look of the Earth's surface was changing. The reds and yellows of oxidized soil, the glint of rusted iron, the sparkle of newly crystallized minerals, a palette born from poison. Oxygen also left its fingerprints in more subtle places. It changed the behavior of trace metals. Elements like molybdenum, zinc, and copper, critical for biological enzymes, began to cycle differently. Some became more available, others less so. These changes altered the nutritional landscape for microbes, pushing evolution in new directions. Even today, the availability of trace metals influences ecosystems, its chemistry with consequences. And the consequences weren't all good. For every species that thrived in the new oxygenated niches, many more vanished. Some went quietly. Others collapsed in dramatic ecosystem failures. Whole branches of the microbial tree were pruned back, never to return. Their metabolisms, once dominant, became rare or isolated. A few hung on in extreme environments, salt flats, anoxic mud, deep sea vents, living relics of a time when the air could kill. But extinction was only half the story. The survivors were different, stronger, more versatile. Life had passed through fire, or rather through frost and oxidation, and emerged more capable. It could now store more energy, build bigger structures, explore more environments. Evolution had been sharpened by catastrophe, and it was only getting started. The Great Oxidation Event didn't create complex life, but it created the preconditions. It didn't build the tree, it prepared the soil, and in the chapters to come that tree would stretch higher than anything cyanobacteria could ever have imagined. But even now, in this chapter of aftermath and reaction, the seeds of the future were being sown. Because once oxygen entered the story, there was no going back. It's tempting to think of oxygen as the hero in this story, the rescuer, the enabler of breath, of blood, of brains. But in its earliest chapters, oxygen was not a gift. It was the antagonist, a shapeshifter, a trigger for crisis after crisis. And like all powerful forces, it had accomplices, As the air grew sharper and the oceans more stratified, a silent army of molecules began to stir. Many of these compounds had never existed in quantity before. Oxidized forms of nitrogen, sulfur, carbon. Some were benign, others were toxic. The chemistry of the Earth was entering an age of unintended consequences. Hydrogen sulfide, or H2S, became a major player. In the deep ocean, far from the reach of surface oxygen, microbes continued breaking down organic matter, using sulfate as an electron acceptor. The byproduct? Hydrogen sulfide, a colourless gas that smells like rotten eggs and kills like cyanide. When ocean currents brought these deep waters to the surface, vast blooms of H2S may have been released into the atmosphere. And here's the twist. Hydrogen sulfide doesn't just smell bad, it's deadly to most forms of aerobic life. It binds to cellular machinery, halting respiration. It can damage DNA, destroy tissues, and kill within minutes. But it doesn't stop there. In high enough concentrations, H2S also destroys ozone, that fragile shield of O3 molecules high in the atmosphere, crafted from oxygen, protecting life from ultraviolet radiation, can be stripped away by hydrogen sulfide. So now we have a double blow, a poisonous gas rising from the ocean, and with it, a thinning veil that once filtered the sun. There's evidence this may have happened more than once. In the aftermath of the GOE, and again during later oxygenation events, sulfur-rich oceans may have burped poison into the skies, triggering mass extinctions. Fossil records show abrupt disappearances. Geochemical markers hint at toxic conditions. Some scientists even speculate that such events may explain certain mysterious gaps in the early fossil timeline. Times when complex life seemed poised to rise, only to vanish. In this sense, oxygen was both cause and cure. It enabled new life, but also set in motion the processes that could kill it. It offered light and breath, but only to those who could endure its storms. Meanwhile, the oceans were caught in a chemical tug-of-war. With oxygen rising in surface waters and remaining scarce below, the seas became chemically stratified. This created a persistent redoxcline, a dividing line where oxic and anoxic waters met. Along this boundary, strange things happened. Nutrients like phosphorus and iron, essential for life, behaved unpredictably. Iron, once freely available in its reduced soluble form, Fe2+, now began to precipitate as rust the moment it met oxygen. This made it harder for surface organisms to access, a kind of nutrient lockout. Phosphorus, too, became trapped in sediments, bound up in oxidized minerals. This scarcity mattered. Photosynthetic organisms need these nutrients to grow. With them, they bloom. Without them, they fade. The biological pump, the process that draws down carbon dioxide and sequesters it in the deep ocean, began to sputter. The balance of gases in the air teetered on the edge of collapse. In short, the rise of oxygen disrupted not just who lived and died, but how the planet itself cycled its essentials. These cycles are not just academic. They are the Earth's internal logic, its silent rhythms. When they stumble, so does everything else. And yet, life persisted. At the margins of these chemical battlegrounds, life adapted. Some microbes learned to shuttle electrons in new ways, hopping between metals, gases, and minerals. Others formed consortia, tightly linked communities where the waste of one became the food of another. Complexity bred resilience. And somewhere in this biochemical wilderness, the eukaryotic cell took shape. It's one of the most remarkable leaps in the history of life, a symbiotic merger between two cells, one engulfing the other without digesting it. The engulfed cell, likely a proteobacterium, found a new home, and in exchange for protection, it offered energy. Using oxygen, it powered the host cell in ways that had never been possible before. This guest became the mitochondrion, and with it cells could get bigger, more complex, more specialized. They could afford to build scaffolding, store information, coordinate internal transport. They could grow beyond the microscopic, They could, in time, become multicellular. But it all hinged on oxygen. Without that molecule, dangerous, volatile, indispensable, none of it could have happened. The emergence of eukaryotes didn't immediately transform the world. For hundreds of millions of years they lived in microbial mats, in the plankton, in the quiet spaces between shifts. But they were different. They were ready. And as oxygen continued to rise, slowly, unevenly, with pauses and setbacks, the stage was being prepared for the next act. Complex life. But first, the Earth had to finish adapting to its own breath. Let's return to the land. For most of Earth's early history, the continents were barren. Nothing green, nothing moving, just stone and wind. But oxygen didn't just change the chemistry of life, it changed the surface of the world. Oxidation hardened the crust, altered soil profiles, and encouraged the formation of clays. These minerals could hold water, bind nutrients, and slowly, subtly, create habitable niches. Over time, weathering brought nutrients into rivers and estuaries, further fertilizing coastal seas. The land and sea began to speak to each other in chemical whispers, and then came the ozone. That strange three-atom molecule was never meant to be part of the plan. It was an accident, a result of solar radiation hitting free oxygen in the upper atmosphere. But that accident was everything. With the ozone layer in place, ultraviolet radiation from the sun was absorbed, reducing the lethal bombardment of the surface. For the first time, shallow water and even exposed rocks could harbour cells without being fried to death. DNA could replicate with fewer errors. Mutations could be inherited rather than immediately punished. This protection was crucial. It meant that life could now inch upward, toward the surface, toward the shallows, eventually toward land. It wouldn't happen quickly. It would take hundreds of millions of years. But the door had been unlocked. All this from oxygen, a molecule so simple, so common, so overlooked, and yet so powerful it could reshape a planet. And yet even now the story wasn't finished, because oxygen didn't rise in a smooth line. It pulsed, it paused, it collapsed and surged again. There were times, perhaps even after the GOE, when oxygen levels dropped. These were called oxygen oases, localized environments where O2 was briefly abundant, only to vanish again. Geologists debate the timing, the scope, the cause. Was it due to tectonic shifts, nutrient cycling, changes in biological productivity? Whatever the answer, the result was the same. Life had to keep adapting to uncertainty, and it did. Through extinction, innovation, cooperation, and sheer resilience, life kept moving forward. Microbes became more diverse, eukaryotes began to spread, small soft-bodied organisms started forming communities, colonies, partnerships, and eventually those communities would build reefs, they would develop skeletons, they would evolve eyes, but that was still far ahead. Here, in the wake of oxygen's first uprising, the world was still reeling, recovering, recalibrating, and in the quiet, life was waiting. To understand the Great Oxidation Event in full, we must learn to see it not as a solitary chapter, but as a verse in a much older, much longer poem, a stanza in the deep rhythmic music of Earth's living history. Because the rise of oxygen, dramatic as it was, did not happen in isolation. It was built on foundations laid long before, and would in turn lay foundations for everything after. Earth's story, after all, is not linear. It loops and echoes. What appears sudden is often the bloom of a buried seed, and what appears stable is often trembling underneath. The Great Oxidation Event, massive, transformative, near-apocalyptic, wasn't the beginning of life's power to alter the planet. It was simply the first time the consequences couldn't be ignored. So let's zoom out. Before the GOE, before cyanobacteria painted the oceans with oxygen, life had already been quietly reshaping the world. The earliest known signs of life appear more than 3.5 billion years ago, microbial mats, isotopic whispers, maybe even stromatolites. These organisms, simple as they were, didn't just survive, they reacted. And as they reacted, they began to change their surroundings. One of the most important shifts in the pre-oxygen era was the emergence of metabolism itself, the ability of cells to capture energy and use it to build, move, divide, persist. Early metabolisms were diverse, experimental. Some cells used hydrogen, others used iron or sulfur. Some pulled energy from ultraviolet light, and each of these strategies subtly altered the chemistry of the ocean, the air, the rocks. Take methanogenesis, the production of methane by ancient archaea. This was not just an energy process, it was climate engineering. Methane is a potent greenhouse gas, and for hundreds of millions of years it kept Earth warm despite the sun being much dimmer than it is now. In fact, without methane, early Earth may have been a frozen rock. With it, the planet remained liquid, alive, dynamic. This tells us something important. Long before oxygen, life was already a planetary force, already altering feedback loops, already playing with fire. Even earlier, perhaps, were the iron breathers, microbes that oxidized or reduced iron in their metabolic cycles. These organisms didn't just extract energy, they left a mark. Ancient iron-rich sediments deposited billions of years ago show patterns that suggest biological activity. Patterns of iron oxidation that make more sense when microbes are involved. In this way, the rise of oxygen was not a new story, but a continuation, an escalation. And oxygen wasn't the first global transformation either. Roughly 700 million years before the GOE, something else happened, something we still don't fully understand. Scientists call it the Late Heavy Bombardment. For a period between 4.1 and 3.8 billion years ago, Earth and the inner solar system were pummeled by asteroids and comets. Entire regions of the crust were melted, oceans boiled, atmospheres were stripped and reformed. Some theories suggest that life may have emerged, been wiped out, and re-emerged again during this violent period. If true, it means resilience is not a trait we inherited, it's one we were born with. In the wake of this chaos, the planet began to settle. Crust solidified, oceans recondensed, hydrothermal systems stabilized. And in those dark, mineral-rich environments, perhaps near mid-ocean ridges, perhaps in warm tidal pools, life found a foothold, or perhaps it never left. This early resilience matters because it set the stage for everything to come. The GOE may have been Earth's first great breath, but it wasn't its first close call, and it wouldn't be the last. Let's move forward in time. After the GOE, oxygen levels rose and then stalled. For over 1 billion years, the air held steady at relatively low concentrations. This time is sometimes called the boring billion, a term that hides its significance behind understatement. Because while oxygen didn't surge, life didn't stop. In fact, some of life's most important innovations began in this lull. Eukaryotes emerged, cells with nuclei, internal compartments, and critically, mitochondria. This symbiosis between an archaean and a bacterium was perhaps the single most important merger in biological history. It created a new kind of cell, capable of storing energy at scale, managing complexity, and eventually giving rise to multicellular life. All of this was made possible by oxygen. It was during the boring billion that sex evolved. Meiosis, recombination, genetic mixing. Another profound leap. And though fossils from this time are scarce, molecular clocks suggest that algae, fungi and other lineages were quietly branching and diversifying, long before their ancestors would be preserved in stone. So the boring billion wasn't boring, it was preparation, slow, burning potential. The planet had taken a breath, and now it was holding it. Eventually, around 800 million years ago, oxygen began to rise again. This second wave, sometimes called the Neoproterozoic Oxygenation Event, set off another series of cascading transformations. glaciations returned, Snowball Earth episodes that may have frozen the entire globe again, twice. But when the ice receded, life came back different. Multicellular organisms flourished. Large, soft-bodied creatures called the ediacarans appeared in the fossil record, some of them over 1 metre long, shaped like fronds or quilts or alien pillows. These were not plants or animals or fungi, but something in between. A biological experiment that would soon be replaced but not forgotten. Then came the Cambrian. About 541 million years ago, in a geological blink, the fossil record exploded. Animals with shells, eyes, limbs, jaws, predators and prey, burrowers and swimmers. This wasn't just an increase in complexity, it was the emergence of ecosystems, food webs, nervous systems, behaviour. Oxygen made this possible. More specifically, the energy provided by oxygen allowed cells to specialise, tissues to develop, and movement to become sophisticated. Muscles, nerves, circulation. All of these require efficient respiration. Without oxygen, there is no speed, no coordination, no sentience. And so, oxygen paved the way for consciousness. It's humbling to realise that the thing we breathe, the molecule that fuels our lives, once nearly destroyed life entirely. It's more humbling still to realise that without that destruction, we wouldn't be here at all. This pattern of crisis followed by transformation is written all across Earth's history. Mass extinctions are not new. They happen in pulses. The Great Oxidation Event may have been the first, but it was followed by others, each with its own cause: asteroid impacts, supervolcanoes, continental drift, methane bursts, runaway climate change. But in every case, life has not just returned, it has reinvented itself. From the Ordovician-Silurian extinction to the great dying of the Permian, from the asteroid that ended the age of dinosaurs to the oxygen pulses that shaped early evolution, life has proven time and again that it can survive catastrophe. And more than survive, it adapts. It's a cycle that feels almost mythological. Birth, crisis, collapse, rebirth. Not because nature is sentimental, but because systems, biological, chemical, planetary, seek new equilibria when disrupted. They reorganise, they shift gears, they test alternatives. And that's what the GOE was, a test, a transformation, a point of no return. In modern science, we talk about Earth system science, the idea that atmosphere, biosphere, geosphere, hydrosphere, and even cryosphere are all interconnected. This is not a new insight. It's simply one we're finally beginning to appreciate in its full complexity. But life knew it all along. When microbes changed the air changed the oceans. When the oceans changed the rocks changed the climate. And when the climate changed, life changed again. These loops, these feedbacks, these chemical conversations, they're not noise. They're the grammar of our planet, and they didn't begin with us. We are late to the story, but not separate from it. Because even now we are part of these cycles. We add carbon to the air. We remove forests that create oxygen. We warm the planet and acidify the seas. The loops are still turning, and we are inside them. The Great Oxidation Event is a reminder that life can alter planets, and that planets, in turn, will alter life. It's also a reminder that extinction is not the end. It is sometimes the only path forward. So when we talk about the GOE, we're not just telling a story of microbes, we're telling the story of possibility, of how life made its first great mistake, and how that mistake became the foundation for everything we now call complex, sentient, beautiful. Without oxygen, there are no plants, no animals, no thought, no love, no song. But before oxygen could build any of those things, it had to kill almost everything else. And yet, in the long silence that followed, in the cold seas and the rusted rocks, life was not finished. It was becoming something more. The story of the Great Oxidation Event is a tale from the deepest chapters of Earth's past, buried beneath billions of years of rock and memory. And yet, the discovery of that story is startlingly recent. For most of human history, we had no idea our world had once been airless, or that a gas as familiar as oxygen could nearly wipe life off the map. The path to that revelation didn't begin in a high-tech lab or with a gleaming satellite. It started with rocks, quiet, unmoving, and very, very old. Geologists have a kind of faith, not in the mystical sense, but in the steadfast belief that rocks hold the truth, if only we learn how to listen. And for more than a century, geologists have wandered the oldest cratons of the Earth, those ancient stable cores of continents that preserve our planet's earlier skin: Canada, Western Australia, South Africa, Greenland. In these places, the crust is not young and folded, but hard and worn smooth by time. It whispers. In the early 20th century, as mining companies sought out iron deposits, they uncovered something strange: rocks layered like ribbon candy, alternating stripes of iron-rich minerals and silica stretching for kilometres. These were the banded iron formations, BIFs, as they'd come to be called, and they were unlike anything forming today. At first, no one quite knew what to make of them. They were clearly ancient, some over 2.5 billion years old. But why the banding? Why so much iron? And why did these formations seem to vanish from the rock record after a certain point in deep time? It would take decades and a revolution in geochemistry to begin to see what they really meant. In the 1950s and 60s, a new generation of scientists began applying isotopic techniques to old rocks. These methods allowed them to peer into the atomic architecture of minerals, to see not just what elements were present, but how they had been processed by the environment. One of the key breakthroughs came with sulfur isotopes. When sulfur is affected by ultraviolet light in an oxygen-free atmosphere, it produces a distinctive isotopic signature called mass-independent fractionation. That signature disappears once oxygen reaches a certain threshold. So when geologists looked at ancient rocks and saw that signature vanish around 2.45 billion years ago, they realized they had found a boundary, a turning point, the before and after of a planetary revolution. At the same time, researchers studying ancient soils, called paleosols, noticed something peculiar. Soils older than 2.5 billion years contained reduced iron minerals, which could only form in an oxygen-free atmosphere. Younger soils were oxidized, rusted red, the same way iron turns red in our everyday world. Everywhere they looked, the same pattern emerged. There had been a shift, a planet-wide change, one so total that it transformed the chemistry of the sky, the sea, and the land. And the only possible culprit? Life. The term Great Oxidation Event was coined relatively late. Before that, researchers spoke in cautious tones: oxygen transition, early oxygen rise, atmospheric shift. But as evidence piled up, rock by rock, isotope by isotope, the conclusion became inescapable. Something monumental had happened, and it had happened because of tiny ancient organisms. Among the earliest champions of this idea was Preston Cloud, an American geologist and paleontologist. In the 1960s and 70s, Cloud argued that the rise of oxygen was the single most important transformation in Earth's history. He called it biological innovation on a planetary scale. His work helped bridge geology and biology, encouraging scientists to think of life as a geochemical force, not just an evolutionary curiosity. Another major figure was James Lovelock, the British chemist who, along with Lynn Margulis, proposed the Gaia hypothesis, the idea that Earth's biosphere behaves like a self-regulating system. While the Gaia concept remains controversial in some circles, it helped open minds to the possibility that life and the planet are co-authors of the same story. By the 1980s and 90s, the field of Earth system science had begun to take shape. No longer were geology, biology, chemistry, and climatology confined to separate silos. Instead, scientists began looking at feedbacks, how oxygen affects climate, how climate affects evolution, how evolution feeds back into oxygen. And still, the rocks had more to say. In South Africa's Transvaal supergroup, researchers uncovered vast successions of sedimentary layers that captured the GOE in action. Each stratum recorded a snapshot of conditions: water chemistry, biological activity, atmospheric composition. It was like reading a novel written in mineral ink. In Western Australia's Pilbara region, stromatolites, fossilised microbial mats, offered a direct glimpse into the organisms that may have caused it all. These layered structures, some over 3.4 billion years old, are among the oldest evidence of life on Earth. They're formed by cyanobacteria, precisely the microbes suspected of releasing Earth's first great breath. Meanwhile, in labs across the world, researchers simulated ancient oceans in glass tanks. They pumped in gases, added minerals, stirred in microbes, and watched how the chemistry evolved. These deep-time aquariums helped test hypotheses that couldn't be proven any other way. Could iron really mop up early oxygen? Could sulfur cycling explain isotopic shifts? How quickly would methane collapse in the face of rising O2? And still, scientists debated. Was the GOE a single event, or a gradual rise with multiple steps? Did oxygen surge in great pulses, spiking, then collapsing again? Was it driven solely by biology, or did tectonics and volcanism play equal roles? Was there a single cause, or many converging trends? Even today these questions are alive. The GOE remains one of the most complex and fascinating puzzles in science, not because we know too little, but because we know just enough to ask better and better questions. And then there are the scientists who ventured out, not into theory, but into the field. Geologists and paleobiologists who travelled to frozen tundras, remote mountain ranges, and sun-baked cratons to chip away at billion-year-old stones. They wore sun hats and parkas, carried hammers and isotope kits, trekked through deserts and climbed ancient ridges, all to recover a few ounces of ancient earth. Rocks that might hold a clue, a ratio, a whisper. One of them was Dr. Dominic Papineau, who explored ancient formations in Canada in search of chemical biosignatures. Another was Dr. Roger Buick, who studied sulfur isotopes in the Hamersley Basin of Australia to understand the timing and consequences of the GOE. And countless more, graduate students, postdocs, field techs, who crouched in silence beside outcrops, brushing dust away from time itself. Their discoveries, though slow and often unglamorous, built the foundation of our understanding. But perhaps the most poetic discovery of all was this: that the air we breathe is not a given. It's not just something that came with the planet. It was earned, built, released and refined by uncountable generations of microbes. It's a living inheritance. And we only know that because someone somewhere picked up a rock and asked, "Why is this red?" That kind of curiosity is deeply human. It's the same spark that led ancient astronomers to track the stars, that drove Darwin to the Galapagos, that sends rovers to Mars and probes to Europa. It is what led us, improbably, to discover a time before the sky was blue. And there's something quietly beautiful about that. Because in the end, what we've discovered isn't just a chapter of Earth's past. It's a reminder that change is inevitable, that even the air can turn against us, that resilience takes time, and that the smallest things, like cyanobacteria, can shift the fate of a planet. And so we keep asking. We keep digging. Because the story isn't finished. It never is. Every discovery about the Great Oxidation Event comes with a kind of humility, not just because of its scale, planetary, atmospheric, biological, but because of how little of it is visible. There are no ruins to excavate, no bones to unearth, no eyewitnesses, just rock, just layers, just faint signatures written in atoms and isotopes, waiting for someone to notice. And noticing takes time. It often begins with something small, a discrepancy in the lab, a field sample that doesn't quite match predictions, a sulfur isotope ratio that feels off, It's rarely a eureka moment. It's more often a slow burn, curiosity flickering into suspicion, then lighting into obsession. The scientists who study Earth's earliest atmosphere aren't doing it for headlines. They work in quiet corners of universities, in field camps far from civilization, in labs where the instruments must be calibrated more precisely than the tools of watchmakers. They publish papers with titles like Evidence for a Paleoproterozoic Shallow Ocean Oxygen Oase, or Redox Stratification at the Archean Proterozoic Transition. Dry titles, maybe, but inside, these papers contain some of the most astonishing ideas ever proposed. That life changed the sky. That air was not always there to breathe, and the people behind them, they are as human as any explorers. Some are sedimentologists, rock readers who can walk up to a wall of stone and tell you its history like it's a diary. They see the crossbeds, the grain size, the subtle hue shifts, and know whether this place was once a beach, a delta, a deep abyss. Others are geochemists, chemical detectives who don't look at the rock but at what's inside it. They grind samples down to powder, dissolve them in acids, run them through mass spectrometers until the ratios of oxygen, sulfur, carbon and iron emerge. It's like eavesdropping on a conversation that ended 2 billion years ago. Then there are the paleobiologists, the dreamers, the ones who look for shape, for structure, for any hint of a fossil in a world where fossils are rare. They study stromatolites, microbial mats, textures so subtle you'd miss them if you blinked. Sometimes they cut thin sections of rock and scan them under polarized light, hoping to catch a glimpse of layered life. Other times they use scanning electron microscopes to probe the nanoscale, looking for cellular patterns, mineral boundaries, things too small to believe and too perfect to ignore. And slowly, across continents and decades, a picture forms. Not everyone agrees on every detail. In fact, the debates can be fierce. Was the GOE truly global, or a patchwork of local oxygen oases? Did oxygen rise in one great leap, or in many steps? Was it driven primarily by biology, or were tectonics and mantle degassing equally critical? Are we seeing the real oxygenation event, or only the moment when it finally became visible? Each question invites a dozen more. But this is how science grows, through argument, through collaboration, through patience. The GOE didn't happen overnight, and neither did our understanding of it. Some of the most profound insights have come not from flashy discoveries, but from painstaking reconstructions, sediment cores taken from drill sites in Australia or South Africa, analysed grain by grain, isotope by isotope. It's slow work, months for a few centimetres, years for a complete profile, but it's worth it. Because those tiny layers tell a story no human ever lived through, but which made human life possible. It's not just a story of oxygen, it's a story of noticing, like when researchers found red beds, oxidised terrestrial sediments, in rocks dated to just after the GOE. That rust in the rock meant that oxygen had reached the land. It was no longer just dissolving into seawater or reacting with iron. It had become ambient. It had begun to change everything it touched. Or when scientists identified the sudden disappearance of mass-independent fractionation in sulfur isotopes. That vanishing act told them oxygen levels had crossed a critical threshold. The air had reached a point where UV light could no longer produce those unusual sulfur signatures. That was not just chemistry, that was atmosphere, that was transformation. These kinds of clues are delicate, but they're also dependable, and more importantly, they're global. Identical patterns emerge in rocks from different continents, different latitudes, different depositional environments. That kind of synchronization doesn't happen by accident. It means something huge was unfolding, something planet-wide, something permanent. That realization has reshaped how we think about life, not just on Earth, but beyond it. Astrobiologists now look to the GOE as a model for how life might signal its presence on other planets. Oxygen, after all, is a biosignature, a clue that something is using light to power itself, and is altering the environment in the process. If we see oxygen in an exoplanet's atmosphere, it might mean something is alive there, or it might mean something once was, but Earth's own oxygen story complicates the picture, because for over 1 billion years life existed without oxygen, and even after oxygen emerged it took hundreds of millions of years before the atmosphere stabilised. So if we looked at Earth during its first 2 billion years, we might see no sign of life at all, a false negative. And if we saw oxygen only briefly, we might assume intelligence, where there was only microbial drift, a false positive. These questions aren't abstract. They guide telescope design, mission goals, the kinds of planets we study, the wavelengths we search. Our understanding of Earth's oxygenation is shaping the way we search for neighbours in the cosmos. But there's a more intimate reason this story matters. It tells us that life is powerful, but fragile. That transformation is possible, but unpredictable. That survival doesn't always look like flourishing, and that flourishing sometimes starts with collapse. The scientists who spend their careers on the GOE know this deeply. It shapes how they think, how they teach, even how they hope. Because if microbes can change the sky, if they can trigger an ice age and still survive it, then perhaps our own challenges are survivable too. Climate change, extinction, ocean acidification. These are our own oxygen events, our moments of planetary risk and consequence. We are now, like those early microbes, altering the air, not with oxygen, but with carbon, not passively, but knowingly, and the Earth is responding. Temperature, ice, weather, fire. The same systems that once shivered in a Huronian deep freeze are now sweating under greenhouse heat. The loops are still running, the feedback still pulse. We too are part of the story, and maybe that's what makes the GOE so compelling. Not just that it happened, but that we found out. That billions of years later, a species emerged that could ask what came before. That could look at a rock and see not just stone, but time. That could put pieces together, not just chemically, but emotionally. There's something undeniably human about that. To walk through the wilderness and spot a layer of rusted stone and wonder, what made this? To pick up a piece of iron and realise it was once part of an ocean. To breathe and understand that the air is not ancient but new, that it was built, that it was earned. This is why we keep going back into the field, why we hike to inaccessible ridges in the Canadian Shield, why we camp for weeks beside iron-rich rivers in Western Australia, why we bore through ancient rock with diamond-tipped drills in South Africa. Not because we expect a grand revelation, but because we are, always, chasing whispers. Because each isotope, each sediment core, each smudge of fossilised mat brings us a little closer to something that no longer speaks. Something that changed the world before words existed. And somehow, that silence still feels urgent. Because this is not a story of what happened. It's a story of how we came to know. And that knowing, that beautiful, fragile knowing, is one of the most precious things we've ever pulled from stone. The deeper we go into the science of the Great Oxidation Event, the more the world begins to shimmer, not with spectacle, but with subtlety. Here, in this quiet complexity, we find a universe of interactions. Atoms dancing through water, rocks telling time, ancient cells whispering across eons through the chemistry they left behind. To understand what happened 2.4 billion years ago, we must first learn to see the world the way geochemists do, not as static terrain, but as an evolving dialogue between matter and energy, between Earth and life, between past and present. Start with a molecule of oxygen. It seems so ordinary. 2 atoms bound together, colourless, invisible, lurking in every breath. But this simple molecule is wildly reactive. Oxygen does not like to sit still. It tears electrons from other atoms. It rusts iron. It fuels fires. It breaks bonds. It is chemically speaking aggressive. This is why its appearance in Earth's atmosphere was such a revolution. For most of the planet's early history, the environment was reducing, meaning it was rich in hydrogen, methane, ammonia, and other electron donors. In that world, oxygen was not just foreign, it was lethal. So the first scientific question becomes, how did such a dangerous molecule accumulate? The answer lies in flux, how fast oxygen was being produced versus how fast it was being consumed. Cyanobacteria were producing oxygen through photosynthesis, yes, but Earth had many ways of removing that oxygen just as quickly. Volcanic gases like hydrogen sulfide, iron from weathered rocks, even methane in the air. All of it could react with oxygen and cancel it out. So oxygen only began to accumulate when those sinks, those removal processes, were saturated. When the world could no longer absorb the overflow, scientists model this dynamic using mass balance equations. They calculate input and output. They track how much oxygen is made by photosynthesis, how much is lost through oxidative weathering, how much is buried in sediments. And through these models, they begin to estimate thresholds. For example, a key threshold is the burial of organic carbon. Photosynthesis produces oxygen, but only if the organic matter that forms, the sugars, the plant bits, the microbial mats, is buried before it's decomposed. If it gets eaten or broken down, that oxygen is consumed again. But if it's buried, locked away in sediment, turned to kerogen or oil or coal, then the oxygen stays in the atmosphere. This is why plate tectonics matter. They control how much sediment is deposited, how quickly it's buried, how continents grow and erode. They also control volcanic activity, which adds or removes gases from the atmosphere. The crust is not just a foundation, it's a lever. It helps set the tempo of oxygenation. And here we enter the realm of deep time feedback loops. Because as oxygen rises, it changes the way rocks weather. And as weathering changes, nutrient delivery to the ocean shifts. More nutrients like phosphorus can trigger blooms of photosynthetic microbes, producing more oxygen. But those same blooms, when they die, can cause anoxia in the deep ocean, and anoxia leads to hydrogen sulfide, which strips ozone, which allows more UV light, which changes surface chemistry again. Everything feeds back into everything else. To track these loops, scientists use multiple lines of evidence: isotopes, sedimentary structures, biomarkers, molecular fossils of ancient life. Each tool gives a slightly different lens. Take sulfur isotopes. These are among the most sensitive proxies for early oxygenation. Under low oxygen conditions, sulfur can exhibit mass-independent fractionation, MIF, a quirky signature caused by photochemical reactions in an anoxic atmosphere. But once oxygen reaches a certain level, around 0.01% of modern levels, that signature disappears. So when MIFS vanishes from the rock record, scientists mark it as the GOE boundary. But there's more. Even after that signature disappears, there are small anomalies, resurgences of MIF in unexpected places. These suggest that oxygen didn't rise in a straight line. It may have pulsed, collapsed, rebounded. This leads us to the idea of oxygen oases, small localized regions, shallow seas near cyanobacterial blooms, where oxygen was temporarily abundant, even if the global atmosphere remained largely anoxic. These oases left behind hints in iron minerals and trace element ratios. It's a patchwork world. Oxygen in spots, like lighthouses flickering across a dark sea. Then there's carbon isotopes. The ratio of carbon-13 to carbon-12 in ancient rocks can reveal how much organic carbon was buried. When photosynthetic organisms fix carbon, they prefer the lighter isotope, C12. If a lot of that carbon is buried, it leaves behind a heavy signature in the inorganic carbon pool, more C13. A spike in D13C suggests a period of enhanced burial, and thus more oxygen retention. Around the time of the GOE, we see precisely this, a massive carbon isotope excursion. It suggests not just oxygen production, but global reorganization, burial, transformation, the biosphere, learning to hide its dead so it could keep breathing. And yet there's nuance. Some researchers argue that these isotopic excursions may also reflect tectonic shifts, changing ocean currents, or volcanic input. So the picture is never static. Each data point is a conversation starter, not a final word. The same goes for iron. Before oxygen, iron in the ocean existed mostly in its reduced soluble form, Fe2+. This gave the seas a greenish tint. But when oxygen was introduced, that iron oxidized, became Fe3+, and precipitated out. This formed the banded iron formations, rhythmic layers of iron oxides and silica. The scale is astonishing. Some of these formations stretch across continents. They're among the biggest sedimentary features ever laid down, but they don't last forever. After about 1.85 billion years ago, BFs largely disappear. Why? Because the ocean had changed. Oxygen had begun to penetrate surface waters more fully, making dissolved iron less available. The ocean had flipped, and in doing so it stopped painting in red and began sketching in chalk. Other geochemical tools help fill in the gaps. Molybdenum, uranium, vanadium, trace metals whose availability is highly sensitive to redox conditions, serve as subtle indicators of past oxygen levels. When oxygen is present, these metals tend to be soluble. When it's gone, they precipitate. Their presence in black shales, for example, can help map ancient oxygen zones across space and time. Then come the biological clues. Molecular fossils, compounds like hopanes and sterones, offer hints about who was living and how. These lipids, once part of ancient cell membranes, survive long after the cells themselves are gone. Hopanes are associated with bacteria, sterones with eukaryotes. A sudden rise in sterane abundance in certain layers may reflect the growing presence of eukaryotic algae, a shift that likely followed increases in oxygen. Some researchers now combine all of these proxies, sulfur, carbon, iron, trace metals, biomarkers, into comprehensive time series. They compare layers from multiple locations, build global maps of ancient conditions, run simulations on early climate and biosphere feedbacks. The result? A picture that is never finished but always sharpening. If geochemistry gives us the fingerprints of ancient oxygen, then radiometric dating is the clock that tells us when those fingerprints were left behind. Without it, the story of the Great Oxidation Event would be a gorgeous but unmoored fable, events floating in time with no sense of cause or sequence. Radiometric dating relies on the predictable decay of unstable isotopes into stable ones. Think of it as listening to atoms whisper secrets across eons. One of the most reliable methods used to date early Earth events is uranium lead dating. Uranium decays to lead through a series of steps with a known half-life, so by measuring the ratio of uranium to lead in zircon crystals, which trap uranium when they form, scientists can determine the crystal's age with remarkable precision. Some of the oldest zircons on Earth, found in the Jack Hills of Western Australia, date back over 4.3 billion years. But for the GOE, scientists often focus on the rocks in the Transvaal supergroup in South Africa, or the Huronian supergroup in Canada. These layered sedimentary sequences preserve a continuous stretch of geological history from before, during, and after the oxygenation pulse. Using isotopic clocks, like uranium lead in volcanic ash layers that sit within these sediments, scientists have bracketed the GOE to between 2.45 and 2.32 billion years ago. There are also iron formations whose ages are pinned down by samarium, neodymium or rhenium osmium dating. These are less precise, but offer key confirmation points, snapshots of a world just before it turned red with rust. Now, with timelines secured, scientists can build atmospheric models, not just of oxygen levels, but of everything oxygen touched. These models are immensely complex and often beautiful in their logic. They incorporate volcanism, weathering rates, biological productivity, burial efficiency, ocean circulation, atmospheric chemistry, and solar radiation. They must also factor in methane, because before oxygen, methane was the planet's blanket. The idea is simple but profound. If oxygen rises, methane falls. And if methane falls, Earth cools. If it cools enough, we get glaciers. This is the essence of the Huronian glaciation, Earth's first known ice age, and possibly its longest. Models suggest it could have been triggered directly by cyanobacterial activity. Life accidentally freezing its own cradle. These are not guesses. They are tested with isotope data, sedimentology, and lab experiments. Simulated atmospheres, reconstructed oceans, sometimes even simulations of entire biospheres. In one class of models, oxygen rises slowly, perhaps over tens of millions of years. In others, it surges in pulses, with feedbacks amplifying or damping the trend. The most recent models suggest a whiplash Earth, periods of anoxia alternating with brief oxygenated intervals, driven by tectonics, nutrient delivery, and biological shifts. This framework leads to the idea of oxygen overshoot, a scenario where oxygen briefly spikes above equilibrium, then crashes as feedbacks reassert control. These collapses could explain the presence of some BFs well after the main GOE window, or the return of mass-independent sulfur signatures in supposedly post-oxygen rocks. And as we peer deeper into these models, one question begins to form. What if this didn't just happen here? Enter astrobiology. The GOE is a Rosetta Stone for those who study life beyond Earth. Because if life on one planet could change the air itself, could tip a whole world toward complexity, then maybe it's not so rare. Exoplanet researchers now look for biosignatures like atmospheric oxygen, ozone, methane, and nitrous oxide. These gases, when found together in the right ratios, suggest biological activity, because their coexistence is chemically unstable. Something must be replenishing them. And Earth's history provides the benchmark. If we detected high oxygen on a distant world, we'd likely think of Earth post-GOE. But if we found only methane, or only ozone, we might be seeing a pre-GOE world. A world where life exists, but has not yet pushed its planet into disequilibrium. There's even talk of exo-GOEs, distant planets currently undergoing their own oxygen revolutions. Maybe their microbial mats are bubbling away beneath strange suns. Maybe they too are on the edge of transformation. But Earth's own case reminds us to be cautious, because biosignatures don't always mean biology, and silence doesn't mean absence. For over 1 billion years, Earth was full of life but would have appeared dead to distant telescopes. No oxygen, no signal, just stone and sea, and that humbles us, because it tells us we might miss others, or that others might miss us. And it also tells us that change is slow, that life's greatest experiments unfold not in years or centuries, but in geologic time, in feedbacks, in thresholds crossed silently, irreversibly. Still, we try to understand. In the lab, scientists now grow ancient analogue microbes in simulated Precambrian conditions. They study how modern cyanobacteria handle iron-rich waters, or how oxygen-producing organisms manage UV light without an ozone layer. Some are engineering synthetic ecosystems to see how oxygen dynamics play out over hundreds of generations. Others probe ancient genes, tracing the molecular roots of oxygen metabolism, antioxidant pathways, and phototrophic systems. By comparing genomes from modern bacteria, they infer which genes might have existed billions of years ago. Molecular clocks, based on mutation rates, suggest that photosynthesis arose more than 3 billion years ago, long before oxygen reached the sky. And all of this converges into a vision that's bigger than Earth science alone. It's a vision of life as a planetary force, not just adapting to environments but building them, not just evolving within worlds, but rewriting their atmospheres, their oceans, their temperature curves. In this light, the GOE becomes more than an event. It becomes a principle, a process, something life might do, given time. a pattern that could repeat under the right conditions elsewhere in the galaxy. And still, there is mystery. There are rocks that don't fit, signals that don't line up, banded iron formations that seem too young, carbon excursions without clear causes, layers of red and grey whose meanings are debated. The Earth does not give up its secrets easily. Sometimes it whispers, sometimes it contradicts, but it never lies. Our task is to listen longer, to model more carefully, to take samples with cleaner tools, to dig deeper into rock, into time, into ourselves. Because the deeper science goes, the more it circles back to wonder that such a tiny organism, a single photosynthetic microbe, could launch a chain of events that chilled the planet, changed the sky, and set the stage for every leaf and lung that followed is staggering, and that we, descendants of that oxygen revolution, can now model it, simulate it, and send messages across space in search of echoes is something close to sacred. We live in the aftermath of a breath that began with sunlight, with water, and with cells too small to see. That breath rusted the oceans, it froze the planet, it shaped the minerals in your bones, and it's still echoing even now. We are, each of us, walking traces of oxygen's long ascent, and we are only just beginning to understand what that really means. When something breaks on a planetary scale, recovery is never immediate. It doesn't surge back like a tide. It creeps like a shadow, hesitates like a breath. And in the wake of the Great Oxidation Event, recovery wasn't a return to normal. It was the slow forging of something entirely new. A planet that no longer resembled its past, with oceans that stung differently, skies that seared more softly, and life that would never breathe the same way again. In the immediate aftermath, Earth was no paradise. Its surface may have gleamed with newly rusted rocks and freshly frozen seas, but for the organisms left behind, the survivors of oxygen's rising tide, it was a bitter inheritance, a world of scarcity, of change, of adaptation under stress. Many lineages of anaerobic microbes, the dominant life forms for over 1 billion years, were wiped out or forced into exile. The few that could survive in oxygen's presence were driven underground, into sediments, into the deep ocean, into pockets where reducing conditions still lingered. Even today these lineages persist, in hydrothermal vents, anoxic basins, marshes and gut flora, tiny relics of a lost biosphere, whispering of a world before breath. For those who remained at the surface, oxygen was more than a biochemical irritant. It was an evolutionary pressure unlike any before. The few microbes that could not just tolerate oxygen, but harness it, began to rise. New metabolic pathways evolved, including aerobic respiration, a method of energy extraction far more efficient than anything possible in anoxic conditions. Where fermentation yielded just a trickle of ATP, aerobic respiration opened the floodgates. More energy meant faster replication, greater complexity, and eventually the possibility of something larger than single cells. But complexity at first remained a distant dream. Earth's biosphere didn't bloom overnight. It faltered, recalibrated. For at least 1 billion years after the GOE, oxygen levels stayed low, enough to alter geology, but not enough to support truly large or complex organisms. This period, sometimes called the oxygen lag, was marked by slow chemical reworking. The deep ocean remained anoxic. Nutrient cycles swung erratically. Mass extinctions may have continued, driven not by cataclysm but by instability. Ecosystems built on delicate, shifting ground. The oceans, once teeming with dissolved iron, became stratified. Surface waters gained oxygen, but deeper layers often turned sulfidic, rich in hydrogen sulfide from sulfate-reducing bacteria. These euxenic conditions were hostile to many organisms and may have stunted evolutionary progress. For millions of years, this redox stratification locked life into narrow zones of habitability, sandwiching it between the burning sky above and toxic depths below. Yet life, patient and persistent, adapted. Cyanobacteria spread, colonizing new niches. Some began forming colonies, offering protection and structural support. Others developed strategies to minimize oxygen's damaging effects. Antioxidants, specialized enzymes, compartmentalized cellular machinery. Then, somewhere in this experimental era, a new player emerged, the eukaryote. With their internal organelles and complex gene regulation, eukaryotic cells were a quantum leap beyond their prokaryotic ancestors. Their mitochondria, descendants of once free-living bacteria, allowed them to fully exploit the energy potential of oxygen. With more energy came more possibilities, larger size, internal complexity, and ultimately multicellularity. It didn't happen quickly. The first eukaryotes may have appeared as early as 1.8 billion years ago, but for hundreds of millions of years they remained microscopic, floating in planktonic obscurity. Evolution, even with oxygen's help, is not a race. It's a long negotiation with time and chance. But gradually cells began to specialize. Some became efficient at photosynthesis, others at predation. Some clung to each other after division, forming filaments or colonies. The first multicellular organisms, simple, soft-bodied aggregates, arose not in a burst but in scattered steps, each one an experiment in cooperation. Meanwhile, the planet itself kept changing. Continents drifted, mountains rose, climates shifted, glaciations returned, including the cryogenian Snowball Earth episodes where ice may have reached the equator. These cold intervals were brutal, but they also cleared the slate, resetting ecosystems and fertilizing the oceans with nutrients from glacial erosion. When the ice melted, life surged, and oxygen, again, played its part. Around 800 million years ago, a second major oxygenation event began, sometimes called the Neoproterozoic Oxygenation Event. This wasn't as abrupt as the GOE, but it was decisive. Atmospheric oxygen crept upward, finally crossing thresholds needed to support larger, more metabolically active organisms. The Ediacaran period followed, marked by soft-bodied multicellular organisms that sprawled across the seafloor like leafy rugs and quilted pads. These weren't plants or animals as we know them, but something in between, a now extinct experiment in form. Their brief flourishing was made possible by oxygen, but they too would be swept aside. Because in the Cambrian, around 541 million years ago, life exploded. Eyes, jaws, skeletons, nervous systems, mobility, complexity in every direction. And once again, oxygen was the enabling agent. Not the cause, but the permission slip. The presence of oxygen allowed cells to work harder, tissues to coordinate, behaviours to emerge. Muscles, brains, blood. They all required high-efficiency energy systems. Without oxygen, there could be no leaping predators, no fleeing prey, no sudden acceleration of life's experiments. From there, Earth entered a new rhythm. Oxygen levels rose and fell, but they never returned to the low ebb of their pre-GOE past. Life, now entrenched in complexity, weathered new extinctions, asteroids, volcanoes, runaway climate events, but oxygen remained a constant partner. Sometimes too much of it caused problems. At other times, its decline signalled ecological crisis. But the biosphere had learned to lean on it, and it never let go. From the first green mats of cyanobacteria to the flowering of forests and the lungs of mammals, oxygen has been both the hammer and the chisel carving out the biosphere we know today. And the consequences stretch beyond biology. The planet's geology was reshaped by oxygen. Oxidized minerals changed soil chemistry. Iron, once abundant and mobile, became locked in rust. The red beds, terrestrial sediments stained with hematite, mark not just a new geochemical regime but a planet with weather, rivers and breathable skies. The planet's climate changed too. Oxygen helped form the ozone layer, shielding the surface from UV radiation and making terrestrial life possible. It also influenced greenhouse gas cycles, indirectly regulating the balance between warming and cooling. Even plate tectonics and mountain building processes may have been influenced by oxygen's role in altering rock properties, water retention, and erosion patterns. And perhaps most poignantly, oxygen left its mark on time. Before the GOE, rocks were dated by their position, their association with certain minerals, or their layering. But once oxygen began reacting with the crust, it created chemical markers that could be measured precisely. Oxidized minerals, sulfur isotope breaks, carbon excursions. These signatures became the calendar of deep time. They are how we know what came when, and they remind us that the Earth is not static. It's not a fixed home with eternal conditions. It is dynamic, evolving, reactive. And the biosphere is not a guest, it is a co-author. The air is not given, it is earned. Even now, the legacy of the GOE touches us daily. Every breath you take contains oxygen produced not just by modern plants, but by the ancient processes those plants inherited. Every cell in your body, when it performs respiration, is echoing a mechanism perfected by microbes billions of years ago. Every rusted nail, every forest fire, every wave breaking white with foam, oxygen is there, reminding us of its double edge, its power to sustain and to destroy. And we, modern humans, find ourselves in an uneasy relationship with this molecule. We depend on it, we protect it, but we also threaten the balance it helped build. We alter the carbon cycle, we warm the planet, we acidify the oceans. These are new kinds of oxygen events, slower, subtler, but no less real. And perhaps, as we peer into the fossil record and reconstruct the GOE, we are not just studying the past, we are rehearsing, learning how life responds to transformation, how it survives collapse, how it recovers. Because recovery doesn't mean going back, it means going forward, reshaped, just as Earth did after the GOE. It means giving rise to new forms, unexpected alliances, emergent systems, like the eukaryote that rose from a merger, like the planet that breathed and then froze and then bloomed. Recovery is not a return to safety, it is a journey through the unknown, and life, if nothing else, is very, very good at that. Sometimes when we talk about ancient events, about oceans gone rust red and microbes that could poison the air, we forget how close those stories really are. We tell them as legends from some other world, unconnected to the warm homes we live in, or the cities lit by neon and breath. But Earth, in its deep time wisdom, doesn't draw hard boundaries between then and now. It doesn't box up its past and put it behind glass. It carries it forward, it folds it into the present, and so, the Great Oxidation Event, that slow catastrophe turned foundation, is not over. It echoes through everything. We don't live in the GOE's aftermath, we live in its consequences. Every forest, every coral reef, every human lung is a continuation of that event, a fragile ongoing negotiation between life and its atmosphere. Which is why, when we look around at the modern world, at rising carbon levels, burning forests, collapsing ice sheets, we feel something disturbingly familiar. The story of life changing the world and suffering from the change. In the Proterozoic, the biosphere altered the air without intent. Microbes bubbled away, releasing oxygen not as an act of engineering but as a byproduct of photosynthesis. There was no plan. And yet the consequences were absolute. The planet froze, species died, but eventually the survivors found a way forward. Life adapted, restructured, evolved. Today the air is changing again, but this time it's not microbes, it's us. We are the new cyanobacteria, only faster, louder, more deliberate. We dig ancient carbon from rock and release it in years rather than millennia. We move nutrients across the planet in ships and planes. We change the reflectivity of Earth's surface, the acidity of the oceans, the flow of rivers, the temperature of seasons. We are now a geologic force, and that should feel profound, not just in a triumphant sense, but in a cautionary one. Because the last time life changed the planet this much, it nearly wiped itself out. We often think of extinction events as acts of nature, asteroids, supervolcanoes, solar flares. But the GOE wasn't a cosmic accident, it was self-made. It came from within the biosphere. Life overproduced, and life paid the price. The comparison is unsettling. Today, carbon dioxide is our oxygen, a small, invisible gas that seems harmless until it isn't. We treat it as a byproduct of energy, of industry, of growth. But its accumulation is changing the rules, tipping balances, triggering feedbacks we don't yet fully understand. And like ancient life, we may find that the systems we rely on, climate, food webs, ocean currents, are not as stable as they seem. This is not to suggest that we are doomed, only that we're not exempt from the laws of planetary feedback. We are not spectators. We are participants in a system that is bigger than our economies, our politics, or our inventions. And the GOE teaches us something vital. Recovery is real, but it is not kind. It takes time. It demands loss. The biosphere always finds a way forward, but it doesn't promise to take everyone with it. In that light, the GOE becomes more than an ancient turning point. It becomes a mirror, a cautionary tale with microbial actors and global stakes. It reminds us that Earth has no nostalgia. It will adapt to whatever new balance we create, whether we survive that adaptation or not. But there's another side to this reflection too, a quieter, more hopeful one. Because the GOE also shows that life can shape planets, that even the smallest, most passive organisms, bacteria without eyes or minds, can change a whole atmosphere. That given enough time, life can build something enduring, something beautiful. If they could do it by accident, then surely we can do it with intention. We are not powerless. We are in fact uniquely powerful. We are the first species to recognize our own planetary influence, to detect the past, model the future, and choose a course. That is unprecedented. We know how carbon moves. We know how warming works. We know what forests mean, what oceans absorb, what species protect. We have data, satellites, computer models, ancient analogues. We are not guessing in the dark. We have the tools if we choose to use them. And we have a responsibility, not just to our children or to the creatures we share the earth with, but to the process itself, to the long arc of life that somehow survived toxic skies and global ice and kept going until it could think and feel and wonder. Because that's what we are. We are the inheritors of that persistence, the conscious bloom of a process that began with sunlight, water, and chance. We are oxygen's legacy. And when we walk outside and breathe deeply, we're not just taking in air, we're taking in history, memory, millions of years of microbial labour stored in every molecule. The oxygen in your lungs right now was made by algae in the ocean or a leaf in the sun, and their ancestors, survivors of the GOE, carriers of the flame. It is strange to feel awe at something as mundane as air, but that's what the GOE gives us. Perspective. It reminds us that the things we take for granted were once unimaginable, that oxygen, which now fills stadiums and forests and classrooms, was once so rare that it could only exist in shallow pools. That life, which now covers every corner of the earth, once trembled on the brink. And if that doesn't humble us, what will? Because even now, there are places on Earth where the old world lingers. In the Black Sea, the lower layers remain anoxic, rich in hydrogen sulfide, home to microbes that remember the past. In the Cariaco Basin, the chemistry still whispers of sulfur. In Lake Matano in Indonesia, deep waters remain iron-rich, untouched by oxygen. These are windows, not just into Earth's history, but into its fragility. They are reminders that oxygen is not guaranteed. It must be maintained, and perhaps so must we. So as we think about climate change or biodiversity loss, or the future of our civilization, it's worth remembering the microbes. They didn't mean to change the world, but they did. And we, who mean to change the world, might yet find the wisdom to do it more gently. The GOE reminds us that survival is possible, but costly. That adaptation is slow, but profound. That even collapse can be a kind of rebirth, but only if something remains, only if we leave room for recovery. And maybe that's the gift of science for sleep. Not just the facts, but the feeling. Not just the data, but the understanding. The softness in the story. The way it tucks into your thoughts like a tide, like breath. Like the memory of a world that learned to breathe. Because we are still learning, still breathing, still becoming. And so, here we are, back in the present, in the warmth of a quiet room, somewhere on a small breathing planet that still holds the memory of rusted oceans, frozen continents, and the first whisper of air. The Great Oxidation Event is behind us, but also around us, within us, in the breath you just took, in the oxygen flowing through your blood, in the plants outside your window, quietly releasing what they don't need, unaware that they are part of an ancient rhythm. What happened more than 2 billion years ago was not the end of a chapter. It was the beginning of possibility. The opening of a door through which life eventually walked upright, asked questions and named the stars. And now, you are part of that story too. If you've made it this far, thank you. Not just for listening, but for wondering, for slowing down, for letting the past drift through your thoughts like wind through trees. If you found this journey soothing, or curious, or quietly overwhelming in the best way, you're welcome to subscribe to stay with us.